Well, good morning, good afternoon, good evening, good tomorrow. I know we've got some people who already know what happened today. So, excuse me. My name's Andrew Best. I'm the Executive Director for Wastewater Education. And every year during April, we do several public outreach seminars, presentations, training classes. Because we really do have that as the second most important thing we do. We do online training and education for anyone in the water and wastewater professions, but we also believe that we have a fundamental right to educate the public, and particularly their elected representatives. Because if they don't understand what we do, how can we expect them to support us? This being April, this being Earth Month, and that becomes even more critical. Some of us are old enough to remember the first Earth Day, which is kind of scary that we're still talking about it now. And we thought it would be a good idea just to remind everybody where we all started. So just give me 1 second here and I will share a video with you.
The 60s brought the flowering of conservation. It was propelled by many things: air and water pollution, sprawl and development, massive fish kills and endangered birds, the Cuyahoga River catching on fire, and oil spills off California and Cornwall. But the real consciousness changer was seeing Earth from space.
In 69 and 70, we started to get real photographs of the Earth from space that completely changed people's perspective on themselves and their role on the planet. They were stunning because you saw a green, blue, cloud-bedecked, living planet in the background with, in the foreground, a dead moon with nothing but craters. The life-death image all combined in one beautiful and compelling scene was what people, I think, began to realize, that we could be the moon. We could be as dead as the moon.
All the social and political ferment that was going on in this country was building up and building up and building up. And on Earth Day 1970, it was like water bursting through a dam.
But I think you have to start out looking at the big picture. The big picture is that we live on a finite planet with a limited capacity to sustain life.
If we do not save the environment, then whatever we do in civil rights or in a war against poverty will be of no meaning, because then we will have the equality of extinction.
Earth pollution is mind pollution.
20 million people came out for the first Earth Day, still the largest demonstration ever. It catalyzed the transition from conservation to a new environmental movement and the next big issue, pollution.
And I wanted to make an acknowledgement here. We have a PBS learning license, and we are allowed to show clips from that video and others, and we are deeply appreciative of that. I do apologize to all the classic car lovers out there who are really a little bit perturbed to see someone taking a sledgehammer to one of those beautiful old cars, but hey, what can I say? At this point, Let's see, the master is recording on, yes. Everyone, there's a message down in here. Who can see your messages? Yes, everyone who posts to everyone can see that. If you want to send a direct message to either me or Kayla, please choose that option in the chat window, and then that won't be broadcast to the room. That being said, I'm going to hand it over to our speaker today, who's Kayla Hansen from Conceal. And once you introduce yourself, Kayla, I'm going to mute myself and turn my video off.
Okay, thanks, Kendra. Everyone, can you hear me?
Yes.
Okay, so I'm Kayla Hansen. I'm an engineer with concrete sealants, and so my background is in civil engineering with an emphasis in structures. And for the last 8+ years, I've worked in precast concrete. My focus has really been on transportation products and wastewater infrastructure. So the transition to Conceal was a no-brainer, and it's so here I am talking about resilience, durability, and ways to enhance water tightness and durability. So with that, I will share my screen and we can get started. Okay. All right, so the title of today's session is Resilient Wastewater Solutions, Building for the Future. So we're going to be talking about resilience in wastewater infrastructure and how these resilient solutions enable us to build long-lasting, durable infrastructure. So America's infrastructure is unfortunately a common theme in the news. It's aging and its condition is becoming more concerning. And I understand that this session is broadcast not just in the US, it's recorded and available to other countries as well. So although during today's session, I will reference facts and figures that are pertinent and applicable to the state of affairs here in the US, the principles and the topics that we're going to discuss, these principles of resilient infrastructure, apply globally. They can and should be used globally. So we've got 4 main learning objectives, 4 key takeaways that I want to share with everyone today. So the first is to explain what resilience is and why resilient construction has become a focal point in all construction lately, but specifically in wastewater projects. Then describe what factors contribute to resilience, what makes a resilient structure, a resilient system, and a resilient ecosystem. Then describe how resilient wastewater solutions can improve safety, reduce construction time, reduce costs, and extend service life. And last but not least, list options for enhancing concrete wastewater structure durability while also reducing concrete's carbon footprint. All right. So I want to start this session out with a little trivia session. It's not so much a quiz and a test of knowledge as it is just an opportunity for us to think about some of these facts and figures that are specific to US wastewater infrastructure. So because we're virtual, you don't have to raise your hand or suggest what you think the answers are, but just quiz yourself in front of your own computer and just give these questions some thought. So question number 1. How many publicly owned wastewater treatment systems are there in the US? Is it 14,000, 15,000, or 16,000? The answer is a little over 16,000. So what this tells us is that there's a lot of maintenance, there's a lot of cost, and there's a lot of upkeep associated with these 16,000 publicly owned wastewater treatment systems. Next question, what percentage of the US population relies on on-site wastewater treatment systems? Is it 11%, 21%, or 31%? This one typically surprises people, it's 21%. And the point here, that's almost a quarter of the US population is relying on on-site systems. And that's a much bigger portion of the population than people tend to think. Now, the third and final question, across all sizes of wastewater treatment plants, systems are operating at an average of what percent of their design capacity? Is it 62%, 75%, or 81%? And the answer here is 81%. So at first thought, you might think, oh, well, gosh, 81%, that's not so bad. That's the best news we've heard so far. But I want to remind you that this is an average. So what that means is that some of the plants are operating at 50% capacity, while others have met or are trying to exceed their capacity. So the point of sharing these statistics in these three questions is to share the scope of the need and the scope of the demand that we're facing. So whether we choose to move forward with on-site systems or centralized systems, and truly it takes a mix, it takes a combination of both on-site solutions and centralized solutions. But whatever the solution is that we move forward with, we've got limited resources and increasing needs that we need to tend to. So it's increasingly important that we look to durable, resilient solutions to meet these needs and to make the most of the resources that we have available. So a few more facts and figures here. All of these statistics came from the infrastructure report card, but and we'll get to that in a minute. But by 2032, it's expected that 56 million more people will attempt to connect to centralized treatment plants. So that's a 23% increase in demand. And if we think back to the last question we just looked at, we're already seeing that on average, these treatment plants are operating at 81% of their capacity. So we're trying to add on another 23% increase in that demand. Additionally, wastewater infrastructure needs, so repair, rehabilitation, and new construction, exceeds $271 billion. So there's a lot of demand here. And third, the Clean Water Act is turning 50 this year. So why does that matter? Well, when it turns 50, it doesn't just expire. The key here is that a lot of wastewater treatment facilities, a lot of treatment plants and treatment systems are designed with a 40 to 50 year service life. So with the Clean Water Act turning 50, a lot of these structures that were put into service around the inception of the Clean Water Act, they are approaching the end of their design life. They're approaching the end of their anticipated service life. So that exacerbates the need for additional construction, additional rehabilitation, additional repair, and additional new construction. So I want to talk a little bit about the infrastructure report card. So ASCE is the American Society of Civil Engineers. And every few years, they assess each state in 18 different infrastructure categories. So it's everything from wastewater, stormwater, roads, bridges, airports, dams, schools, levees, you name it. So they assess each state on these different categories and they give them a grade on an A, B, C, D, or F scale. And overall, the US's grade for wastewater infrastructure is a D+. And it sounds pretty abysmal, and it is, but it's actually improved over the last couple of years. Previously, it was like a D or a D-, but these grades are really eye-opening, and the information that they have on their website is really telling. So what goes into one of these grades? Well, let's take a look at this here. So the first factor that they consider is capacity. So does the infrastructure's capacity meet current and future demands? What about its existing condition right now, as well as its near future physical condition? What about funding? What is the current level of funding from all levels of government for this infrastructure category compared to the estimated funding need? What about the future need? So what's the cost to maintain and improve the infrastructure? Will the future funding prospects address the need that exists, or will we have a deficit? What about operation and maintenance? What is the owner's ability to operate and maintain this infrastructure properly? And is it in compliance with government regulations as codes and standards change? What about public safety? To what extent is the public safety jeopardized? Hopefully not at all, but to what extent is the public safety jeopardized by the condition of this infrastructure, and what could be the consequences of failure? We'll talk about failure a little bit more later. Additionally, what about innovation? What new and innovative techniques, materials, technologies, delivery methods are being implemented to improve this infrastructure? And last but not least, resilience. What is the infrastructure system's capability to prevent or protect against significant and multi-hazard threats and incidences? How able is it to quickly recover and reconstitute critical services with minimum disruption, with minimum consequences to public safety and health, the economy, national security? So what is resilience? Well, resilience is the capacity to adapt to changing conditions, and it's the ability to maintain or regain functionality and vitality in the face of stress or disturbance. It's the ability to bounce back after a disturbance or interruption. It's also the ability to absorb or avoid damage without suffering complete catastrophic failure. And it's the ability to rebuild or repair faster and for less cost. And it gives us the ability to adapt to changing needs, because the needs that we have today aren't going to be the same needs that we need to keep in mind in 10 years, 20 years from now. So it's the ability to adapt to changing needs. It's the ability to regain and maintain and regain functionality in the face of adversity, and the ability to rebuild or repair faster and for less cost. So resilience provides protection against natural and the unfortunate man-made disasters, including fires, hurricanes, floods, tornadoes, earthquakes, extreme heat, and terrorist attacks. And in resilient design, we want failure to be predictable. Okay, so we want failure to be predictable, and we want to make sure that it's not catastrophic. We want it to be proportionate to the cause or less severe in comparison to the cause. So we don't want it to be disproportionate to the cause. The double negative is kind of confusing, but essentially what this means, this can trip some people up because we're talking about being able to predict failure. So in design, there are certain, we anticipate certain loads, we anticipate certain forces and certain flow rates, certain volumes. There's certain things that we anticipate, and we know that it's going to be a certain amount, and then we bump it up a little bit further so that we can have a little more conservative, a little more of a conservative approach. And then on top of that, we add in factors of safety to make us even more prepared for these outliers and these extreme conditions. But when we're talking about failure being predictable, what we mean is that if something were to happen, we want to know how it's going to fail. We want to know how the structure or the system is going to behave when it's exposed to these really extreme conditions and these extreme environments, so that we can, kind of have a warning sign. We know, okay, something's about to happen. Let's take it out of service. Let's shut things down. Let's get people to safety so that we don't have a catastrophic incident. So the two examples that I have here are a rubber band, very simple example, but when you stretch a rubber band, it gives us a warning sign that that when it's approaching its peak amount of stretch, we know that it's going to fail, and it gives us a few indications that it's going to do so. So one, it becomes harder to stretch. The further you stretch it, it becomes harder to stretch, and the material starts to thin out. It starts to neck a little bit. So it gives us that warning sign. And the same thing is true in this other example. I really like this one on the bottom right here. This is a precast pre-stressed double T beam. And the interesting thing about this is even under this extreme load, the significant amount of weight that this beam is carrying, it deflects so much. It bends and deflects, and to the point where it touches the ground, and it still has not had a catastrophic failure. So it gives us an indication that something's going on so that we can remedy the situation before it becomes catastrophic. So making sure that when we are designing these structures and when we are designing these systems, that we are anticipating failure. And you might ask, well, if we can predict failure, then why don't we design these structures and these systems so robust that we never have a failure? Well, at some point you get you reach a point of diminishing returns. It just becomes so costly and they're so over designed, and you're never ever going to experience that extreme case. So by planning for some outliers, putting in really conservative factors of safety, and designing with resilience in mind, we can gain those benefits without all of that extreme cost. So really it comes down to a combination of sustainability and durability. So we're building with durability as our focus, but we're applying sustainable principles. We're trying to use sustainable practices. So this is a really good example of resilience that I always bring up in these discussions. So Hurricane Katrina, if for the US audience, this is going to be a really familiar discussion topic, but Hurricane Katrina made landfall in the Gulf Coast of the US, specifically Louisiana, Mississippi area, on August 29th, 2005. This photo was taken on October 5th, 2005 in Pass Christian, Mississippi. So this photo was taken almost, over a month after Hurricane Katrina made landfall. And the one thing that I want to point out, this entire neighborhood was absolutely decimated, complete devastation. All that remains that we can see here from this entire community is just the concrete slabs where these houses once stood. And all that remains in this community is this one concrete house. So this house was built in accordance with FEMA standards. And although it's complete devastation, there's no doubt about that. But this family is able to rebuild faster than the other families in this community. They have less extreme devastation. They have something to come back to, and that they can build off of, that they can start to rebuild their lives. So this is a perfect example of resilience. It's enabling this particular family to bounce back faster and with less cost and with slightly less disruption than the rest of the community, because this house was built with a robust design using durable materials and durable strategies. So what are resilient design principles? There's a Resilient Design Institute, and they've outlined a variety of principles to help us achieve resilience in design. And the first one is that resilience transcends scales, and this includes both size and time. So what this means is we can apply resilient design practices on a small scale, from something like the chemistry of materials, all the way up to a structure, to an entire system, to a community. So it transcends scales. It's not just all or nothing. It also, the other scale that it transcends is time. So there are short-term things that we can do immediately, and then there are longer-term things that we can plan for and build up to. Additionally, diverse and redundant systems are inherently more resilient. So when we're talking about design and redundance in design, the one example that I always like to use is a bridge truss. So if a truss in a bridge a single truss would fail, the entire bridge isn't going to come crashing down. That would be incredibly catastrophic, incredibly dangerous, and way too risky. So there's redundance in that design. So if one of those members or one of those components of the truss would fail, the system is still going to stand up. It's still going to be fine. So having diversity and redundance in these systems will make them more resilient. It'll make them more likely to stand up to adversity, whatever that may be. Additionally, simple, passive, and flexible systems are more resilient. So the more bells and whistles and contraptions and more reliance that we have on electricity and Wi-Fi and things like that, those are all things that could fail. Those are all things that could go wrong. So when we're relying on simple or passive systems, like relying on gravity separation in a septic tank, or relying on a leach field, for example, to treat some of this effluent, those are passive systems. They just happen on their own. We don't have to interrupt them. We don't have to hope that the generator kicks on and keeps everything up and running. So when we have these simple and passive systems, they're more resilient. Additionally, durability strengthens resilience. So, we're talking about resilience as a combination of sustainability and durability. And the key here to resilience is, standing up to adverse conditions and being able to rebuild faster in the face of adversity. So when we have durable, strong, long-lasting materials, that enhances the system's resilience. Additionally, locally available, renewable, and reclaimed resources are more resilient. Whenever possible, we want to source these materials, source these structures, source these solutions in our local area. We don't want to have to rely on shipping something halfway across the globe to achieve this solution. Additionally, resilience anticipates interruptions in a dynamic future, right? So that's what we've been reiterating a few times now, is that we want to prepare for the unexpected. We want to prepare for changing needs. We want to prepare for outliers and be able to stand up to them and withstand them in a way that we can bounce back faster after those threats have passed. Additionally, we want to find and promote resilience in nature. So the last presentation that we had actually was about constructed wetlands. And when we see something in nature that works well, humans often copy it. And it's not just, it's not just specific to wastewater. It's true in a lot of different capacities. Think of, camouflage, or think of, the design of airplanes, for example. So whenever we can find resilience and success and ease in nature, we want to mimic it if we can. And resilience is not absolute. It's not all or nothing. It's not something that we have to go from 0 to 100 immediately, or we're never going to have any improvement. There are small steps that we can take to make a difference and start to make our infrastructure more resilient. We don't have to go from 0 to 100 immediately to see improvement. So why does this all matter? Well, our infrastructure is aging, populations are increasing, demand on systems is increasing, and there's limited resources to rehabilitate and replace current infrastructure, and there's limited resources to build new infrastructure that meets our changing needs as society evolves and grows. And natural disasters are increasing in number and severity. Now, even if money grew on trees and we had unlimited resources there, it still wouldn't really solve these root problems and provide solutions to these challenges. So it comes down to money, time, materials, and manpower. So we need to do as much as we can while conserving resources, while also making these solutions last for generations to come. And it sounds daunting, and at times it can be, but it's completely doable. It's completely feasible. We know how to do it. We have the roadmap to achieve this. So how do we do that? Well, resilience really needs to be the goal of design, the goal of maintenance, and the goal of restoration for both individual structures, entire infrastructure systems, and entire communities. And it begins with comprehensive planning. And this also means stricter codes and standards that will produce more robust structures, that will produce more robust systems that have long service lives. And a lot of times people think, well, gosh, codes and standards, don't like that. It just makes my job harder. But so when we talk about stricter codes and standards, the concern is that it's going to make people's jobs harder. And that's not the intent. And that's not really realistic. So the idea behind that, by making codes and standards more robust, is to give us better solutions, to challenge the status quo and make us think of, all right, these are some better raw materials that we can use. These are some stronger design philosophies that we can implement. And not just thinking about satisfying our current need, but also thinking about long-term solutions. So some of the other ways that we can achieve this is by prioritizing projects that focus first and foremost on safety and security. So prioritizing projects that improve safety and security of systems and communities to ensure continued reliability and enhanced resilience. Also improving land use planning across all levels of decision making and striking a balance between the built environment and the natural environment. Also including or enhancing natural or green infrastructure projects, and that comes to play a lot in on-site applications. So what factors will contribute to resilient wastewater structures? Well, first and foremost, it starts with material selection, then structural and system design, manufacturing, installation, and maintenance. And we're going to talk about all 5 of these subtopics a little bit. So first up is material selection. So when we're looking for materials to build these wastewater systems with, we want to select materials that are strong, that are durable, that are appropriate for their intended use, and that have sustainability and their environmental impact in mind. We want to make sure that we're selecting products that will stand up to the environment that they're going to be exposed to for their entire service life. We want them to provide durability. We want them to provide long service lives. We want them to be able to resist these harsh conditions and be able to bounce back. Then talking about strength and durability. So specifically in wastewater applications, we need these materials and these structures to be resistant to leaks, right? They have to be watertight. We need everything that's inside these structures and these systems to stay inside these structures and systems until they're ready to go out through the intended outlet. And we need everything that's outside of these systems to remain outside of the systems. We don't want any infiltration or exfiltration because, one, it could disrupt if water, rainwater, whatever, infiltrates the tank and comes inside the tank, it'll disrupt the treatment system that's going on inside the tank. And of course, we don't want anything outside the tank to leak out of the tank because it could contaminate the surrounding environment. So these structures need to be resistant to leaks. They need to be resistant to freeze-thaw cycles, abrasion, chemical and biological attack, thermal fluctuations, and impact, just to name a few. So we're talking about resilience being a combination of both sustainability and durability. So it's important to also think about the sources of these raw materials. There are naturally occurring raw materials that work great. There's recycled options, there's man-made materials, and we want to think about the energy intensity of the manufacturing process of these materials. And whenever possible, source these raw materials locally. Now, when it comes to the design of these wastewater systems, we have to think about strength, water tightness, capacity, resistance to buoyancy, ease of maintenance, safety, modularity, and ease of installation, future need, cost, and service life. There's a lot of factors that come into play here, and we're going to talk about each one of them. So first up is strength. When it comes to the design of these structures, first and foremost, it has to be strong. So we need to follow applicable codes and standards, and we have to select design options that will withstand the anticipated loads. We know these service conditions, we know the environment that these structures are going to be installed in, and we also need to be prepared for these outliers. Even when we incorporate factors of safety into the design, there's always going to be an outlier, so we have to be prepared for that. So thinking about depth of bury, the soil loads, the hydrostatic loads, where is this water table when it comes to these underground structures? Sometimes we have to consider traffic loads and impact loads, and of course we're always taking into consideration a factor of safety. Now on the far right here, I have a screenshot of ASTM C1227. So this is a product standard for precast concrete septic tanks. And this outlines requirements for raw materials, for the manufacturing process, testing, design, dimensions, you name it. So following these standards, following these codes and standards helps ensure a certain level of reliability, right? So if anybody's just making a septic tank and not really following any particular roadmap to success, we don't really know what we're getting in terms of quality, reliability, and service life. So following applicable codes and standards is critical in these applications. So we also need to design for water tightness, of course. So we want to select designs and materials that enhance the water tightness to protect not only the integrity of the system and the performance inside the treatment system, but also the surrounding environment. We want to keep what's in the tank, and what's outside of the tank, right? So this is also going to impact the health and safety of the surrounding environment too. So we want to choose dense materials. When in wastewater applications, if we're choosing strong, dense, durable materials, water, wastewater, and contaminants are less likely to penetrate those walls. So dense materials, low permeability, low porosity, those will help enhance the water tightness of these structures. And in many applications, we can choose density enhancing and water tightness enhancing options. And we'll talk a little bit more about that near the end. In addition, we can also take some additional measures to help damp proof and waterproof these structures. So what about capacity? We're talking about codes and standards and regulations, and there are, of course, sizing regulations as well. They're, at least in the US, they're generally pretty consistent, but there is some variation from state to state. But we want to make sure that we're selecting design options that, of course, meet our current needs, but also that will accommodate future needs, that will accommodate some growth. And we can have too much of a good thing. We can oversize these systems as well, and we don't want to do that, but we want to be reasonable. We want to accommodate some reasonable growth as well. Now, what about buoyancy? Typically when people think about buoyancy, we think of things that float in water or air. But in the case of buried structures, in the case of underground infrastructure, we can have instances where these structures float or shift depending on the water table and the soil conditions and the weight of these structures and the amount of soil that's backfilled and that they're buried under. So we can have instances where these structures will float, pop up out of the ground, or shift if we don't account for those buoyant forces properly. So we want to make sure that we're selecting design options that will resist these buoyant forces, select options that are, remember we're talking about how passive systems, passive and simple systems are inherently more resilient. So selecting options that are inherently resistant to buoyant forces, so denser, heavier materials when these structures are buried. So providing fail-safe resistance to buoyant forces. And we want to be able to withstand these forces that would arise in certain out of the norm conditions. So you have a 100-year storm. We already have a high water table. We want to make sure that even in these outlier, even in these extreme cases, that we're able to resist these buoyant forces. We also want these structures to be easy to maintain. This is a huge part of resilience. We don't want to have to go back and constantly repair things or constantly install something that's new or updated. We want them to be low maintenance. We want to just set it and forget it, with the exception of some routine preventative maintenance. So we want to select design options that are low maintenance, they're inherently strong, durable, resistant to harsh environments, and they don't need a lot of routine work just to keep the design operable. And we want to select options that enhance the structures and the system's durability and its service life. So this will in turn provide low maintenance costs and a lower maintenance frequency while giving us a long service life. We also want these designs to be safe. It seems so simple, but specifically when we're talking about underground structures or buried infrastructure, a lot of times we'll need to have, they'll need to be designed to withstand traffic loads. So making sure that these designs are in fact traffic rated when needed. We also want redundant safety features, and we talked a little bit about that earlier. But if one system, if one of the safety features were to fail or not be operable, we want something else there to back it up. So we're talking about the bridge truss example again. So that brings up this circular yellow contraption. So this is specific to underground structures, specifically to septic tanks. But this is a secondary safety device where if the lid were removed or damaged or whatever, it somehow wasn't keeping the septic tank contained, that this secondary safety device is installed underneath the lid so that if the lid was damaged or removed or not replaced, then it prevents animals or people from falling into the tank. And because oftentimes we know that if that happens, if a child or animal would fall in the tank, oftentimes they lose their lives. So having redundancy in design and in safety is really important. And we want to make sure that, again, that we're being able to withstand these extreme or out of the norm cases. And if they do fail, that the failure is predictive. It's not absolutely catastrophic. We know how it's going to fail. We know what's going to happen and we can plan for it. Also, selecting design options that are modular and easy to install. This is a huge one. So if we can select design options that are quick to install on site with a whole bunch of these features installed at the manufacturing facility before it even gets to the job site, it results in less labor on the job site. So less cost, less time, and less labor on the job site. And when we're able to install these things faster, when so much of this is already done, it's all modular, it's all done before it even gets to the job site, we can close up this excavation faster, we can shut down this construction site faster. So that results in cost savings and it really improves safety. We don't have this excavation open. We're not using all of this expensive equipment for days, weeks, months longer. It's done pretty darn quickly, pretty efficiently. So when we can have modular designs and components that are pre-assembled, pre-installed before they even get to the job site, that also enhances resilience. We also want to think about future need. So again, selecting design options that will accommodate future needs within reason, because we can't predict everything, and we can over design it to the point where we're not really getting anything back out of it. So we want to make sure that we're designing for future needs as best we can and trying to make these designs adaptable. If they can be and if possible, making them so that they can be retrofitted to accommodate those changing needs or changing capacities in the future. A big one is the cost as well. So I like this iceberg image here because, a lot of times when we're thinking about the cost of repair, rehabilitation, or new construction, we really just first and foremost think about the acquisition cost. What is the upfront cost of implementing this solution? Well, there's so much more to it than that though, right? We have to think about the costs that exist below that water line. So think about the maintenance needs, think about upgrade costs and frequency. What are the operation costs? What do the inspections, how frequently do we have to inspect it? What do the repair costs look like? What does the disposal cost look like at the end of its service life? So a lot of times, and I'll pick on asphalt versus concrete roads, a lot of times cities, municipalities, they will, if the roadway conditions are just atrocious, there's all sorts of potholes, at least in the Midwestern US, that's a big issue every year. But asphalt is cheaper up front in comparison to concrete, but the service life isn't as long. So a lot of times to make the most impact in a short amount of time with as few resources as possible, cities will repave roads with asphalt, knowing that, hey, this is a cheaper solution, but it's not going to last very long. And they know when they go into it, they know they're going to have to repair it or replace it in just a couple of years, but they're trying to do what they can with limited resources but it doesn't solve any long-term problems. So sometimes it makes more sense to invest more upfront, knowing that we're getting what we pay for, knowing that we're getting a more durable solution, we're getting a longer lasting, a significantly longer lasting solution. So we have to consider, when we're talking about costs and we're talking about service lives, we have to consider durability, we have to consider the entire service life of this system, and also consider optional enhancements that can extend the service life and reduce those below the waterline costs. So if we can pay more upfront, but we know we're getting what we pay for, we're getting a really durable, robust solution, a really durable, resilient system, and we know it's going to last, you know, significantly longer than other options, then that will contribute to a resilient system. And opting for these optional enhancements, which again come at an additional cost over the alternative solutions, this can really extend service life. It can really enhance durability and resilience. And again, service life. So we want options that are going to last a long time. We don't want to have to come back and constantly repair something. We don't want to have to come back and replace it in just a few years. We want to select options that will stand the test of time and not just serve the immediate need, but that will serve the need for generations to come. Now, manufacturing is another factor in resilience. So we're talking about production processes, manufacturing duration, quality assurance, quality control, and testing. Now, QA and QC are two totally different things. So quality assurance is all process oriented, and it's all about preventing defects. It's a proactive approach. Quality control, on the other hand, it's product oriented. It's all about going back and, okay, we implemented these processes in quality assurance to try to prevent any defects, but now we have to go back and check our work. We have to go back, check our finished product, and try to identify any defects. It's a reactive strategy, but together, you know, we need both of them. Together, they make a complete system, and they help ensure that whatever goes out onto the job site, whatever actually gets installed and provides this solution, that it's going to meet our needs, it's going to meet our expectations, and it's going to check all these boxes. So when it comes to installation, it's always, always, always critical to follow the manufacturer's instructions and industry best practices. So it's important to consider in terms of installation. It's, you know, probably not something that people typically think of when we're talking about resilient solutions and selecting resilient design options, but it's important to consider construction time, transport distance. Remember, we're talking about choosing options that are locally available whenever possible. We also want to think about handling, setting, and bedding foundation and backfill requirements. So when we talked about resilient design principles, one of those principles was selecting passive, simple solutions. And when it comes to installation, sometimes these installations can just become so complex, they turn into engineered solutions instead of engineered, or excuse me, they turn into engineered installations instead of engineered solutions and engineered products. So selecting options that have more passive installation, they're inherently strong, durable, and dense. They're not going to move around. They don't need all sorts of bells and whistles to keep them in their place. And of course, maintenance. We want to select options that are low maintenance. We want to use routine, scheduled, and proactive inspections, but we want to select options that reduce the frequency of those inspections in the first place. And we want to have timely maintenance with proper repair materials and proper repair procedures. So with that, we've talked a lot about, a lot about concrete wastewater infrastructure, and something specific that I wanted to call out is precast versus cast in place concrete. So precast is manufactured it's produced in a manufacturing facility in a controlled environment. The fresh concrete's poured into forms, it's allowed to cure, and it's stripped 24 hours later. And then this structure is transported to the job site at a later date versus cast in place, where the concrete is poured into its final location and it cures out in the field, out on the job site. So because precast concrete is cast and cured in this controlled manufacturing environment with diligent QA and QC, in some cases, we can actually have thinner sections and less concrete when we're using precast as opposed to cast in place. So a resilient solution here could be to use precast as opposed to cast in place in certain applications. Additionally, because it's manufactured in a controlled environment, oftentimes it can be constructed faster with less disruption and less cost and enhanced safety because the construction happens quicker. There's less that needs to be done on the job site. That excavation doesn't need to be open as long. And again, because the concrete is cast and cured in this controlled environment, we were able to optimize all of the characteristics of these raw materials that go into making a batch of concrete. So in some cases, or in a lot of cases, you'll get greater strength, you'll get enhanced durability, you'll get reduced permeability and enhanced water tightness with precast as opposed to cast in place. Additionally, we can also have reduced life cycle costs because the concrete is more durable and it is more robust and resilient. So some of the options here specific to concrete that can help reduce the concrete's carbon footprint and keep sustainability in mind is to use supplementary cementitious materials. They're also called SCMs. So these are used in conjunction with and as a partial replacement for ordinary Portland cement. So they enable precast producers or concrete producers to reduce the amount of cement that's needed, and that in turn will reduce costs. And interestingly, they can help increase the density of the concrete as well. So that in turn will lead to reduced permeability and enhanced durability and water tightness. So there's a variety of them here, and they can be used in precast or cast in place. It's applicable across the board. So some of these names might sound familiar. There's fly ash, slag, silica fume, and metakaolin, just to name the few most popular ones. Another option is to use limestone cement. So limestone's a naturally occurring material in Portland cement. And typically there's a maximum of about 5% limestone by weight in cement that goes into concrete. But now there's a push to use type 1L cement or limestone cement that has a greater limestone content. So this helps reduce the carbon footprint of the concrete because there's less of the energy intensive material goes into making the cement. So they hold back on some of the other materials and put limestone in, and it's ground really fine to help offset some of the lower strength, so it doesn't impact strength or some of the other characteristics as much. Another option is to use durability enhancing admixtures. So chemical admixtures are used in just about every single concrete mix, whether it's cast in place or precast, and they're used for a variety of different reasons. Sometimes to enhance the end product performance, and sometimes to just make it easier to work with on the job site. So some of the options that are specific to wastewater infrastructure are densifying admixtures, MIC protection, microbial induced corrosion of concrete, so protection against that. Also using air entrainment and water reducers, as well as corrosion inhibitors. So there's a lot of ways to internally inherently enhance the durability and robustness of the concrete itself before you even get to things like the structural design or the installation. There are also options for adding coatings or sealants to the exterior surface to provide damp proofing or to provide waterproofing, or again, MIC protection. So some of these products can also protect against growth of fungus, mold, or algae. So there's a lot of different integral and exterior options to enhance durability and enhance resilience of these structures. So all of this comes to play, and all of this really begins with having well-informed stakeholders. And that's what we're all here doing today. We're learning about what our options are. We're learning about some of the challenges we're facing, and we're learning about the solutions that exist. So I thank you all for taking the time to join this session today. So resilient wastewater solutions, it really begins with strong, durable, watertight structures. They're sustainable, they provide engineered solutions that are adaptable, they're economical, and they're built with the future in mind, and they're always advancing. So with that, I thank you for your time, and it looks like we've got about 5 minutes for questions. So I see a couple things in the chat function here. If we don't have time for all the questions, or if you think of some other questions later, feel free to reach out to me via email or give me a call. Otherwise, let's see here. Oh, no questions yet. So Dendra, is there anything else?
Yeah, just a couple things. Let me put my video back on here. Thank you so much. I was thinking while you were talking there about resources that have already been used and resources that are still in real good working order. One of the attendees today is our board member, Sam Lyons, who did a wonderful class for us on the history of concrete and cement and precast, and that many of those structures are still being used. People are still going to the Colosseum in Rome. People are still going down to the catacombs. People are still enjoying those Roman roads. There was a fabulous online course that I took from, I think it was FutureLearn, about the Roman port of Portus, or the invention of marine hardening concrete. Talk about a sustainable option that began centuries ago. If there are any questions, please put them in the chat window. If you would like to be unmuted and speak, let us know. Okay, we do have one question here from Samarine. I hope I'm pronouncing that right. Great presentation. I have a question. How often SCM are being used in wastewater infrastructure?
Oh, that's a good question. I don't have any, firm specific data on that, but I would imagine that they're being used very frequently. So the way that some SCMs, the way that pozzolanic SCMs work is they react with some of the other cementitious products and they react with some of the stuff that doesn't do a whole lot in terms of providing strength or density, and they make more of the stuff that does provide strength and density. Excuse me. So the way that these SCMs work, they inherently, or the pozzolans, they inherently densify the concrete. So I would imagine that they're used pretty frequently. It also depends though on the geographical area, because a lot of SCMs are industrial byproducts. So fly ash, for example, comes from coal. And as coal is being used less, there's less availability of fly ash. So there are other options. So in some cases, using integral admixtures can help offset that, so we're not relying on resources that are less readily available.
And just for the benefit
Thank you so much.
of any of the public that are watching this at a later event, there's been a lot of concern about large deposits of fly ash that in themselves are becoming a problem. I'm sure they can be reused in the manufacture.
I'm so sorry. So I guess it probably, I can't speak with certainty to that, but I would imagine that some of those fly ash deposits can still be used. There are a lot of requirements that they have to use. We can't just like dig up any old fly ash deposit and go ahead and use it. It needs to meet certain standards for quality and purity and make sure that there aren't imperfections in it that will detrimentally impact the concrete, for example. But yeah, does that answer your question? Kind of.
Yeah, I think it goes to the heart of your presentation about sustainability and resiliency. Human beings are pretty smart, and they have a way of finding their way out of horrendous situations. And you know, on that note, I don't see any other questions coming in here. I did want to give a plug, and let me put it into the chat window here. We have a partnership with Operators Without Borders. As I'm sure you're all aware, most of the infrastructure in the Ukraine has been damaged, if not totally destroyed. They are currently putting together a mission later this year to move into a bridgehead, shall we say, in Poland, and they are hoping to recruit individuals who would be willing to form a corps to go back in and help rebuild the infrastructure in Ukraine, hopefully after the end of hostilities there. So I just, I did want to put that in there. If there are no other questions here, I want to just share the closing slide from your presentation. Just a second.
Oh, do you need me to stop my sharing?
No, that's okay. I did that. Okay, so thank you all for attending. We really appreciate you coming today. We are an education organization. If you have a subject that you believe is important for the public to be aware of, please contact us. We would love to host that on our public education forum. I want to thank Kayla again. Thank all the people who recommended you as a speaker for today. And with that being said, let me stop sharing here. Not seeing any other questions coming in. I'm going to say thank you to everybody and end the recording. If you would like to stick around and have a conversation afterwards, we will be here for the next few minutes. Otherwise, thank you so much and goodbye, everybody. We'll see you again next time.